Hello and welcome to another coding session. How about that? But you didn't expect that shit to happen. Yet another session. It's every day, bruh. Yikes. So today is Thursday, if I'm not mistaken, and that means today, according to the schedule, we are supposed to be doing HTTP library in C development, but yesterday I had so much fun developing my own programming language that I decided to make another episode of a programming language development. Yes. Even my neighbors are super excited. Anyway, so you can find the source code of this language in the description. It's completely open source. It's available on the GitHub. There we go. And on the previous episode, we started to what did we do? Yeah, I think we were improving the parser. And the reason why we were trying to improve the parser is because we needed a better compiler messages, because I believe compiler messages are extremely important for a good programmer experience, right? Because basically a software development is a conversation between a compiler and programmer. So the compiler assists the programmer, and programmer moves forward, unless you're programming in dynamic scripting languages. So previous episode is going to be available in here. And so the question is, what we're going to be doing today. So our language currently looks like this. So it's only capable of doing very simple things. It can have an entry point, and it can write things to the standard output. That's the only thing it's capable of right now. So I was thinking that maybe the time has come to introduce more constructs to the language. This language is not Turing complete right now. Right. So to be Turing complete, I think it needs loops, conditions, and some variables, right? And once we have those, maybe it's going to become a Turing complete, right? And the way we're going to demonstrate that is probably we're going to implement something Turing complete, right? It's either could be a Turing machine, or a game of life, or rule 110, like any Turing complete system. If we can implement that Turing complete system in this language, we can say that, yeah, it's probably Turing complete. So yeah. But some people, of course, is going to be like, actually, your computer is not Turing complete because it doesn't have an infinite memory. Yeah, sure. Anyway, so what we're going to introduce in here, I think I'm going to introduce if conditions, right? I think if conditions are quite important for a good software development, right? For a good experience during software development. It's kind of difficult to develop like useful programs without the if conditions. So maybe that's precisely what we're going to implement right now, right here, right now, right here. So we're going to start with the elseless condition, right? Elseless condition is the condition that doesn't have else. That's why it's called elseless. Right, so, and the reason is because like elseless condition is a little bit easier to parse. You don't have to think about, you know, nested stuff. For example, if you want to do something like this, you know, we'll see. But maybe we're going to support like a Python style elif. Yeah. Oh, by the way, the mod, the highlighting mode that I use actually supports elif, and the highlighting mode that I use is nim. Well, the reason why I'm using nim is because like I don't find nim particularly interesting, like particularly special language. It's an interesting language, but I don't know, I hate all of the languages equally, so it doesn't really matter for me. But it supports highlighting of a keyword proc, and I wanted to use that word. Right, because in my opinion, programmers did a pretty shady thing. They stole a notion of a function from mathematicians, right? So basically, before programming, word function meant a very like specific thing. It meant like a mapping from one set to another, and mathematicians were using this notion for quite some time. And then programmers came in and they stole this thing, and now function is all of a sudden a sequence of instructions that can have an input and an output. And also all of a sudden functions may have side effects, and because of that we need to introduce like a special notion of a pure function and whatnot. Like, no. if these things are not a mapping from one set to another, it's not a fucking function. Let's call them procedures, right? Some procedures may have arguments, right? Some procedures may have the output. Like, it doesn't make them functions in the mathematical sense, right? So they are procedures. So I don't know, maybe in this language we're going to have a notion of a function, but if I'm going to introduce the notion of a function, it's going to be a mathematical notion, maybe pure function, or always going to be like a func. Surprisingly, nim also supports func. Right, and basically these functions are going to be absolutely pure and they're going to be suitable for compile time evaluation or something like that. But at the same time, I don't see anything wrong with functions with side effect executing at compile time as well. It could be useful at the build step, right? So you're trying to compile the program, it does some side effects, maybe just gathers some information in the file system and bakes that into the final executable. There's nothing wrong with that. So yeah, you can also make procedures work at compile time. Anyway, the question is what func means in terms of like in the context of nim. Func keyword, interesting. Special syntax to declare the semantic of a func keyword. I suppose it means precisely what I meant, right? It's basically yeah, but I mean, it's just some sort of a discussion. Anyway, whatever. If you're interested in nim, I'm gonna put it in here, nim programming language. Oh, speaking of nim programming language, by the way, the tool that I use to zoom in and do this kind of effects and stuff like that is called Boomer, because it's Zoomer application. Yeah, so it's like it's called Boomer, right? It's called Boomer, and the reason it's called Boomer because it's a Zoomer application for Linux, and it is written, believe it or not, in nim, right? It is written in nim. So, and if you're interested in using this thing, you can find it in here. So I'm gonna put it on Boomer. There we go. So here it is. So give it a star, of course, if you like this kind of application. Smash like and subscribe. All right, so what I was doing, I think I wanted to introduce if construction to the language, right? So let's try to introduce an if construction. Maybe I need to fetch the other stuff just in case. Okay, fetching the latest stuff. It's actually the latest stuff already. Bang if, right? So this is going to be the branch that we're going to be developing in. And let's try to rebuild everything just in case. Just in case. So everything. Absolutely fucking everything. Everything built successfully, and maybe I'm gonna also always rebuild only two tools, BME and Bang. Bang is the language compiler, and BME is an interpreter of the virtual machine, the bytecode of which is the target for our language. So let me try to do that. So then I'm gonna do build toolchain Bang, and I'm going to try to build some examples in here, and the example is going to be hello Bang, and the only thing I want from this thing is a failer, right? I want it to fail telling me that expected, okay, so it actually successfully parsed if, right? Because from the point of view of the parser, if is just a name, right? It is just a name, but then it failed like around here. Oh yeah, it recognized it as a function call. Yeah, this is actually very interesting. It recognizes it as a function call because there is a name, and then comes the parent and stuff like that. So yeah, this is basically a function call. I wonder if we can utilize that. So, but then it actually failed. Oh yeah, because this thing got recognized as a name too, so it expected another parenthesis in here, so we can just make it like that, and that will advance the parsing. Of course, all of that is incorrect, right? And also you have to, oh shit, like, yeah, this is how you need to develop Yeah, finally we advanced the parsing, because right now we can only parse string literals, right? Only string literals and function calls, right? So this is the function call with a single string literal, and this is another function call with a nested function call. And then it fails around here because it expects like a semicolon or something, right? Because it expects it at the end of the statement, and if I put a semicolon in here, it will fail with a known function, I'm pretty sure. Okay, so yeah. But as you can see, our compiler isn't capable of parsing these kind of things, and that's precisely what we need to do in here. We need to teach teach the compiler how to parse this kind of stuff. All right, so let's go to the source code of the compiler. So it's going to be src toolchain bang, and yeah, let's go into the parser. Let's go into the parser, and in the parser, we probably need to introduce a special AST node, right? We need to introduce a special AST node. So we have bang statements, and right now, bang statement can only be an expression, right? We need to introduce a new kind of bang statement, and it's going to be if. So let's quickly do that. So it's going to be type def struct bang if, and the bang if is going to consist of two things right now. It's the condition, right? So on condition is going to be bang expression. So here's the condition, here's your condition, and then branch, because we are doing elseless if for now, so we're only going to have like the then branch. So and the then branch is essentially going to be, I suppose, statement, right? It's going to be a statement. And I suppose since this thing may become self-referential and infinitely grown structure, maybe statement has to be actually a pointer, right? So it's going to be something like that, which also implies that then can be missing. But it's going to be super useful for else branch, right? It's going to be super useful for else branch because else branch might be missing. That makes sense. I wonder if you can allow a missing then branch. That would be actually kind of interesting. So imagine, let me show you. If, else. And this entire construction would basically act like unless from Lisp, right? You have a condition in here, right? And this entire construction is basically like unless. But what's interesting about that is that like it's syntactically consistent with the rest of the things, right? You have like then, and if you don't really care about then, instead of having unless, you can just have if condition else. It's kind of dumb. I'm not sure if I'm going to support that, but that's an interesting thing, isn't it? It's like, yeah, you can have if without else, but why can't you have if without then? Right. So why do we only allow if without else? Why not just allow if without then as well? And syntactically, it will just look like this. And it's super easy to convert this like this condition into an opposite one by just adding else, right? In case of unless, you will have to go remove the word, do unless. No. Here you can just add a new word, right? And then remove. Isn't that cool? I know that it's a dumb idea, but yeah, it's just something interesting to explore from the syntactical point of view. Anyway, so if we ever want to implement that, we can just quite easily do that, right? Because then can become null, and that's it. Anyway, so now bang if itself can be an expression, can be a statement, not an expression. So bang if. This one is going to be if, and unfortunately in C if was already taken, so we have to call it if. So, and here is an interesting thing. This is precisely why I wanted to make it a pointer, right? Because if this thing will not become a pointer, bang statement includes bang if, which includes statement, and this basically creates a recursive structure that is infinitely grown in memory. So you won't be able to even do that. And also maybe we need to forward declare the bang statement. So let me quickly do that. So it's going to be a type def struct bang statement. There we go, and it's going to be just bang statement. And here maybe we can just move this entire thing in here, and there there we go, there we go. All right, so now we have a recursive definition and stuff like that, but we need to actually distinguish between these kind of statements, right? We need to be able to distinguish between them, and I suppose we need to introduce some sort of like a union, all right? Actually, not union, but you know, kind of the statement. So let me quickly do that. So probably can be something like type def in num bang statement kind, right? And I really don't like the word statement because it's very, very long. It's a very, very long name, and I wonder if we can actually shorten it up. STMT. Is that a word people use to shorten up statements? I think it is. I think that's what people quite often use to shorten up statements. So maybe this is precisely what we're gonna do. I wanna actually Google it up. STMT statement. Okay, so at least in PHP, people do use this kind of like abbreviation. Yeah. So as you can see, it's like an industry standard in PHP. So, and if it is an industry standard in PHP, we should use it as well, right? STMT. All right, so this is going to be abbreviation of the statement. So what I'm going to do now is I'm going to quickly replace all of the occurrence of the word statement with STMT. So a query replace statement STMT. Actually, I'm going to do that without any case statement. STMT. There we go. Boom, 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 boom. And we already have like a abbreviation for expressions. And you know what's cool? This makes expression and statement have the same length, and it actually looks nice. I really like that. This is perfect. Thank you, PHP. PHP is the language of gods. Thank you for introducing such a beautiful industry standards. We're gonna use this abbreviation from now on. My God, absolutely beautiful. All prize PHP. Okay, so that will break a lot of code, right? That will break a lot of code because the code right now depends on these things being called statement. But we're gonna follow the compiler-assisted refactoring. We're gonna follow all of the compilation errors. We're gonna fix them, and everything is gonna work first try. Trust me, I'm a professional software developer. All right, so let me try to rebuild this entire stuff. Real fucking quick, mate. Real fucking quick. Okay, so let's query replace a statement with STMT, and I also renamed a part of the function. Maybe that's precisely what I want, because quite often here we also abbreviate to expr, which is totally fine. So maybe because of that, look, there's a little bit of inconsistency. So compile bang expression into bosom, compile statement into bosom. Why don't we call it bang statement? Right, and why don't we call it bang block? We can do all of that, but that will introduce more seeds for the compilation errors, for compilation error threads, and it may become a little bit overwhelming. So let's not do it right now. Right, we can do that a little bit later. It doesn't really matter. Okay, so another thing we need to do in here is that. Okay. So this one, super quick. All right. So, and in here, we're gonna replace it. So next one. Cool. So we made it work. We made it work. So what we did in here, we just renamed statement to STMT. Oh boy, oh boy. Where is my soy? So I already started to do a little bit like of these things in here, which makes it kind of difficult to separate all of that into different commits. So maybe I'm gonna go back into the bang parser, actually bang parser.h, parser.h, and just remove. I don't really know, do I want to remove it right now? So I think I do want to remove it right now and just put it into like a temporary buffer in here. So now this entire thing simply looks like, you know, like it looked before, just with the renaming, right? And also with additional tab depth, but that doesn't matter. That doesn't matter. All right, so let me see. So everything looks okay. So now I'm gonna do a commit, rename statement to STMT. Perfect. Let's actually push that. Let's actually push that. Okay, so let's actually go back into introducing a new thing in here. So this one is going to be something like this, right? And this one is going to be something like this. And again, we need a special thing to distinguish between different kinds of statements. Because of that, we'll have to introduce enumeration, bang, stmt kind. And right now we have a bang stmt kind expression, right? So expression could be a statement by itself, right? Then if, right? And do we need anything else? We don't need anything else. We just introduced like a little thing in here. All right, so statement, let's introduce bang, statement kind, right? And now we have a kind, and depending on this kind, you have to choose between like these two things. But we kind of want to make a union out of these two things, right? So maybe because of that, we'll need to introduce something like type def union, which includes these two things, but we'll need to give it a name. So I'm not really sure what to give here. So the entire thing probably could be called something like unwrap, right? Because it's sort of wrapped into a typed pointer, and we sort of unwrapping it. So let's actually call it, I don't even know, bang stmt unwrap. It's kind of I don't even know. No, let's call it unwrap. It's kind of dumb, but I mean, it is what it is. Right, because if you have a bang statement, right, if you have a bang statement, something like this, right, and it's initialized with something, whatever, what you're going to be doing, you're going to be checking its kind, right, and if it's kind equal to bang's statement kind if, what you will do, you will take this statement, unwrap it as if. Shit. This is genius. What if we rename this thing to as? Look at that. So you can now say a statement as if, almost like you're like converting it. And this entire thing could be just something like as. This is actually goddamn fucking cool. This is a pretty cool pattern. Right, so you have a union, and then you like check its kind, and then you say statement as if. It even reads like English. Holy shit! And then you can say statement as expression. And as we have more different kinds of statements, you can just. This is so cool. I like that. And thank you so much that the as is not a keyword in C, because it is in a lot of languages these days. Right, so yeah. Well, I mean, if it was a keyword, we could always easily do something like as, right? So it could be as. So it's an as pattern in C. I mean, if as is taken, we could just take it like as. Haha, funny joke. My god. Anyways, so I think I established the naming in here. Alright, so we have a kind, this is a union, and let's try to compile this entire thing and see where it fails and follow the compilation errors and fix everything. Whoa. Okay, so I think I put something, yeah, so this has to be a comma. It has to be a comma. And this is precisely what I mean. So statement as expression. Beautiful. Absolutely fucking beautiful. I really like it. This is genius. Okay, as expression. And okay, everything compiles, only our language is molding, but that's fine, that's expected. So Parse, so let me see. So we do have a parse statement, right? Parse bang. I don't see it. Where is parse bang funcal? I think it goes somewhere in, yeah, so we'll probably do it in the prog def. Right, we're doing it in the prog def. Okay, let me actually follow this entire thing. So here's the prog definition, and then we parse in the curly bang block, and inside of the curly bang block, we actually parse in the statements, I suppose, right? Are we? Are we? I think we do. Parse bang. Yeah, okay. So that's what's going on here. I think we need to introduce a special function to parse statements, because right now this code is written so we always expect a semicolon at the end of the statement, like always, which is not necessarily true. Like we don't need to expect that for ifs, right? So we don't really need to do that. But in any case, whatever. So let's introduce statement, but yeah, let's go introduce that. So it's going to be bang parser. It's going to be bang stmt, right? Parse bang stmt. Arena, and we're also going to provide the lexer, because this is the source of all the lexems, which we're going to use in our parsing. And I don't know where I'm going to put that. Let's put it somewhere nearby the while loop, all right? Somewhere here. And I'm just not sure where I'm going to put the semicolon. Is it going to be inside of this function or outside of this function? It's kind of hard to tell. Maybe it's going to be inside of that function. Yeah, probably. All right, so in here, what we need to do is, yeah, we're allocating this thing. We're creating this statement and whatnot as expression. Yeah, so let's actually do it like this. Oh, and also we forgot to set up. The kind of this expression, right? So it's going to be bang stmt kind expression, right? So it's quite important to set this thing up. Let's do it like this. We're going to set up bang statement, right? So this is going to be statement, and it's 0 initialized. All right, and in here, for now, we're only parsing the bang stmt kind expressions, right? So that's the only thing we're doing as expression, and we just parse bang expression using the arena and the lexer that were provided in the arguments in here, right? So they're provided in the arguments. And after that, I think we just expecting semicolon, right? So we're simply expecting a semicolon and just disposing it, and then we are returning the statement itself. There we go. So that way we can tuck all of that code under this function, right? So we allocated the node, and then we do stmt equal parse bang statement, right, from the arena and the lexer, right? And we don't need this kind of stuff anymore, and we probably don't need this kind of stuff anymore, right? So we just allocating the node, parsing the statement, and then appending all of that to the linked list. All right, so, and this is where we're gonna add additional code to parse if conditions, right? This is where we're gonna put all of that. So essentially we'll have to take the first token, right? We have to look ahead, and if that token is keyword if, right? If it is keyword if, we're going to parse this thing as an if construction. If it is not, we're going to try to parse it as the expression. So that's going to be precisely the idea. But let's check if this entire thing compiles. Okay, it compiles, but I mean, our language failing, but that's expected. That's expected. So let's do the following thing. Let's commit all of that. So introduce if construction to the bang AST, and AST stands for abstract syntax tree. And if you never heard about AST, just Google it up. This is not how we Google that. AST, right? Abstract syntax tree. You see how easy it was? You just Google it up and just, you know, appears in your search, you just click it, and now you know what is the abstract syntax tree. There you go, AST. So yeah. The idea essentially is that you have a text, you parse it and turn it into tree, and the compiler actually traverses that tree, generating the code. Compiler never like traverses the actual text, because actual text doesn't really make much sense to the compiler. First, it needs to be turned into a form that is understandable by the compiler, right? And this is how your code usually looks in the memory of a compiler. So it works only on trees. Right, and by like interpreter will traverse this tree and interpret it, like act accordingly while it's traversing it, and the compiler will just generate code while traversing it. It's like a very oversimplified picture over compilers and interpreters, but roughly that's what it is essentially. So compilers and interpreters are just glorified tree traversals. That's what I always say. They're just glorified tree traversals. If you can traverse a binary tree, you can implement a compiler. Trust me, it's as easy as that. Sorry. Cheers. All right. So what we need to introduce in here, we need to start to finally parse if conditions. Right. So we already prepared the statement, and first thing we want to do, we want to check the next token in the Lexa, right? So let's take the bang token, right? Bang token, here it is, here's your bang token. And then in Alexa, we're going to pick into the next token, right? So we're providing the Alexa and we're providing the pointer to the output token. If this entire thing reached the end, we're going to throw an error. We're going to throw an error saying that try to parse the statement, but reach the end of the file. That's it. So that's precisely what we're going to say. std error bang lock fmt error tried to parse, and let's put it this way, expected statement but reached the end of the file, right? So and then we're going to do something like bang lock arguments, right? Bang long arguments, and we're going to extract end of file location, right? So in that location is going to be something like bang lock end of file location, bang lexer location, right? So if you reach the end, you will be pointed at the end of the lexer, so it should be fine. So this one could be also const, and after that we can just exit with non-zero exit code, and that's totally fine. All right, so after that we can dispatch upon different kinds of the tokens. So let's do a switch, right? So it's going to be token kind, and what kind of tokens do we even have? Let's take a look at them. So we have roughly 7 kinds of tokens. So I guess right now we only care about name. Yeah, maybe in this particular case we don't really need to do the full switch, right? We can do the following thing. If token kind is equal bang token kind name, and quite important, token text equal to if we found a keyword, right? We found a keyword. Right, and that means here we'll try to parse this thing as an if condition. So we'll have to do stmt kind bang stmt kind if, right? And then it's going to be stmt as if parse bang if let's actually put it this way, arena Lexa. Since we picked this token, it's not going to be removed from the Lexer, and this function will have an access to the if keyword to verify that it's doing everything correctly. And after that, we can just return the statement. Maybe because of that, I want to take this entire thing and just, put it right here, because why not? Excuse me. It's kind of strange that every time I do something like this, it doesn't... Look, here is relative position 10. Right, I say move up 10 times, but it doesn't do that. It always jumps one behind, and that never happened before. I don't know what exactly is going on here. It just like never jumps precisely there, which is really strange, which kind of defeats the purpose. But I mean, it works for 1, right? So here is 1, I jump 1 up and it works. And here is 9, I jump, let's actually put 10 just to be sure 100%. It's really weird. Something is really weird with Emacs. Anyway, so if so we have this thing. If the token that we found is a name and that name equal to if, right, we're just trying to parse it as if. Otherwise, right, we're trying to parse it as an expression. So that makes sense to me, I think. So, and also maybe I want to actually do it like this. There we go. All right, that is very, very cool. And also for expressions, we always expect to have a semicolon at the end. All right, so let's actually implement this function real quick. So it's going to be something like this. Bang, if arena bang Alexa. All right, so, and let me just try to see if all of that still compiles. Is not implemented yet. Void arena and another one is going to be Alexa. All right, so I think I also need to forward declare it in the header. Let's quickly do that. Of course, semicolons. Almost. Almost first try, almost got coder. All right, so everything, okay, so and it fails here because it's not implemented yet. All right, so the thing we're gonna do in here, we need to take the token, le token, all right, we need to take le token, it's gonna be 0, and we need to expect the keyword if. Bang Alexa, bang Alexa, bang Alexa. Expect keyword. Yeah, that's precisely what we need in here. We need to expect the keyword. Expect the unexpectable. So this is going to be the Alexa, and the keyword that we're expecting in here is going to be if, right? So we're expecting this thing in here. And what's interesting is that I think we also need to keep track of the location of the statement, right? We need to keep track of the location of the statement because we're going to be using it quite often. And I think we kind of already do that for the function calls. Yeah. We do that for the function calls. But interestingly enough, do we need to do that for all the statements? So I'm just thinking, do we have to keep track of the statements on the level of the bang statement, right? Like right here, maybe we need to put like a bang lock in here, or should we actually keep track of the locations like on the level of each specific thing, right? Like expression or if. I think we need to track them on the level each specific thing because we usually need locations when we have a lot of information to actually dump for the user, right? So when we're doing something specific with the if condition, we're deep down into the abstractions and we know specifically that we're working with if. And this is precisely the place where we need to know the location of the if. So the location of the if is better be somewhere in the if itself, in the bang if itself. So we might as well actually put like a bang lock in here, right? So it's better be here because I quite rarely would need it in a higher level, so I'll probably need it inside of if. So yeah, and the same goes for the expression, but right now I only need that for the if. All right, so we're gonna have a bang if, and this is gonna be just 0, and of course we'll need to return this entire thing, so we just return if. There we go, and after that If everything went okay, this line won't crash, and if it didn't crash, that means we can just grab the token's location and assign it to the location of the if. There we go. You know, for this kind of structures, it would be better to have special constructors, because quite often I have a problem that I'm modifying the structure, right? I'm modifying the structure, adding like a new field in here, but I forget, but I cannot easily find all of the places where the structure is constructed to, you know, include this thing into the initialization, right? It would be way better if we had something like bang if, make bang if, right? Where you would get the constructors, right? So the condition, the then, else, right? And then instead of like directly initializing the structure, we would create it like this. And then if I add a new field that needs to be taken into the account, I could just add a new argument in here, right? And it will break all of the places that use this constructor, right? That use this constructor. And then I can go through all of them and do the compiler assisted refactoring. So maybe that's precisely what I need to do in here. Because it will make it a little bit easier. To be fair, to find all of the places where I initialize the structure, I can probably rename one of the fields, and I know that this field is usually used in the initialization, and I will go through all of these places and just update them. Maybe that's could be a solution for this kind of thing. I don't know. I don't know, depends on what precisely you need, so I'm not gonna think about it too much right now. So here's the if location, so we found it, and then we need to expect a token, right? So this is gonna be a token, and what kind of token do we expect? We expect bang token kind open open parent, right? So here's the open parent, and then we're going to have a close parent. So we have open and close parent, and between those things, we're going to be trying to parse an expression. So it's going to be if condition bang parse bang expression, and we're going to pass arena and Alexa. There we go. So here's our condition. My God. All right, and the next thing we need to do in here, we need to parse the then, right? And then is essentially just a curly block, right? And we have a special function to parse the curly block. Here it is. Right, so curly block, we're going to provide the arena, we're going to provide the Alexa, and there we go, we have a then. We don't have an else yet. We don't have else yet, but we're gonna have it at some point, right? So to do bang if construction does not support else. There we go. So this is gonna be to do, and we're gonna fix that a little bit later. All right. So I suppose we successfully fixed this entire shit, more or less. And yeah, let's keep compiling. Let's keep compiling. So what do we have in here? So, oh yeah, block. Oh my god, oh my god, oh my god. I see. So I think in bang if this should not be a statement. This should be actually a block. Yeah, that's right. And block is a sequence of statements. Okay, that makes sense. Thank you so much, Mr. Compiler. Very cool. All right, bang unknown type bang block. Is it called something else? It's called bang block, but it's unknown. Very, very interesting. You know what? It's kind of difficult to, you know, keep track of the types and how they're interconnected together. It would be way better if we just forward declared all of them up front, like in num bang expression kind to bang expression kind like this, and then we would have a version of these things like that. Right, so maybe we're gonna have like two sections. First we forward declare all of the types, and then we just define all of these types, and that way it's relatively easy to have interconnection between them. Right, so I think that's what we need to do in here. Because yeah, that would be actually kind of useful, I think. So let me quickly put that. C programming language, am I right? C programming language. Type def struct bang fun call. Bang fun call. There we go. Oh boy, oh boy. Where is my soy? It's gonna be something like that. In the modern programming languages, you can just, I mean, C is just like a single pass compiler, right? So that's why it needs forward declaration and shit like that. But, yeah. But Zosin, in Rust, in Rust, you can do that and that and that. Zosin, use Rust. I'm sorry. Yeah. Rust. We're almost done, I think. Yeah, so it's almost like a little bit of the type defs, so this is gonna be like that. No, can we even like sort them? If we try to sort them, sort lines, it actually sorted them by enumeration, structs, and unions. Oh my god, would you look at that? That's actually pretty cool. But that's not what I wanted actually. So another one. I'm gonna just copy paste it in here, and boom, there we go. I might as well, oh okay, I think I can just quickly jump between type defs and whatnot. So, and then it's gonna be 5. Next type def. Right, and I'm gonna go back into this type defs. Look at that, look how efficient all that is, my god. So did I, it's a statement as, type def statement as is, okay. Alright. So we can destruct. What am I doing with this? Alright, so let's put it like this. So yeah, we're forward declaring everything. Everything is almost forward declared except of this last thing. Hopefully that I'm not gonna break too much in here. I really hope so. The last type def, I'm gonna put it in here. All right, so shit. Compilation. Let's try to compile it and see if it compiles. Okay, finally. So it actually forbids forward reference to enums. The fuck? I need to make a small break. I'm sorry. Alright, so let's make an exception for the enumerations, alright? So it's only needed for self-referential situations, right? And enumerations can refer to anything, so maybe it doesn't really matter for enumerations specifically. So we can just remove that. So we're only gonna forward declare the structs and unions, and for the enumerations, we're gonna leave it as it is. Alright, so useless storage class in empty declaration. Yeah, I do agree with that, but it was not that. It's not what you think, Mr. Compiler. Just got another Chatterbait donation. I get this one like pretty much every stream at the same time. So yeah. Thank you, kind sir. All right, so what do we have in here? Another useless forward declaration, okay. And this one is another one. You know, this is what happens when you try to copy paste shit too much. But I mean, that's why we have a compiler. A compiler tells me all of that, right? So the compiler just tells me all of that. Okay, so let's actually go to these enumerations, right? So here is enumeration, and let's just like type def it right here. So again, for enumerations, it just doesn't matter because they're not referring to anything, so they cannot be self-referential or anything like that. You can just like define them in place. All right, so there we go. Is it gonna compile now? Hopefully, we'll see. We'll see. Okay, so it compiles. Nice, beautiful, 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 beautiful. All right. So, what was the next thing I wanted to do? I kind of forgot. What I wanted to do. I think that is it. I think, right? I don't see anything special in here though. So if I take a look at the compilation, so here it says expected. Okay, so we only can parse right now function calls with a single argument and string literals. Right, so to make the parser actually advance properly, we need to actually put this through like this. Right, so let's see what's gonna happen. Okay, perfect. Yeah. So we reached the unreachable state, which is kind of interesting. Because we're compiling expressions. Oh yeah, we're compiling expressions, but we don't know how to compile different kinds of statements. Yes. So we'll need to introduce a special thing in here. So it's going to be something like switch statement kind, right? And let's take a look at different kinds of the statements. So I'm going to go to the parser, right? And where are the statement kinds? STMT kind, there we go. So we have expressions and ifs. Right, it's going to be case, and we're going to replace commas with colons. There we go. And this is where we are compiling the expression. Right, so we already passed the parsing stage. We are actually compiling the AST. So we need to implement a function that says compile bang if into bosom, right? So we're going to provide the bosom context, and then we're going to take the statement as if. Actually, it's called if because if is already taken a keyword in C, and we also have to provide write ID. It's basically an ID of a native write function. It needs to be passed everywhere because we don't have a name table for different native functions yet, so it's a like quick temporary hack. And let's make the default branch in here. So essentially, if you reach the default branch in here, that means you have a weird value in kind, and usually it happens when the memory is corrupted somewhere. So we need to assert this entire thing like this, saying that 12 back unreachable. There we go. And then I'm gonna break this entire stuff. Not really break. I think I need to exit with 1. There we go. I need to exit with 1. We had some warnings though. So this function is not implemented yet. Okay, so let's actually implement this function specifically. Compiler. Let's put it in here. This one is going to be void. Not void, but just void. Bosom. So then we're gonna have something like bang if, and this one is gonna be native ID. By the way, that's kind of weird that I have to write it from scratch. I could have. All right, so let's actually put it in here, and let's just say that it's not implemented yet. Bosom if write ID. And in here is going to be, let's go up to grab this assert. Compile, there we go, compile bang, then 5, and then go back in here, is not implemented yet. Where is the compilation mode? Okay, here it is. Okay. It's hard. Programming is hard. You know what else is hard? Oh, I'm sorry. All right, so this is not implemented yet. How are we gonna implement all of this stuff? Right now, we're kind of making an assumption, right? We're kind of making an assumption that else is null, right? So else is null. So let me see. So you have a condition like this, and then you have the whole block, right? In terms of like bosom, right? In terms of like bosom, you need to compile condition, right? So you're gonna have like a condition pointer, and this is like a condition instruction. So it's gonna be instruction, 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 and so on and so forth. Right, and then we have a body in here. Then the body starts somewhere here, right? So here is the body, and here are the instructions of the body, right? Instructions of the body, and then here is the body end. This is where the body ends. So essentially, you have a condition, and if it's true, we have to let the execution fall through this entire thing. If it's false, we have to skip to the end. So we need to take the condition and negate it, right? So it's opposite one, and jump to the body end, right? So that means if it's true, it's going to be false, so it will skip this jump instruction and fall through the body. If it's false, it's going to become true, and that means it's going to actually jump over the body. So basically, this is what we need to compile this thing into, right? Condition is going to have its own sequence of instructions, and body also going to have its own sequence of instructions. We need to establish these 3 points. And stuff like that. To be fair, maybe we don't even need to know this thing. Maybe we don't even need to know this thing. Interestingly enough, what we can do in here, so we can just compile the condition. Compiling the condition will just append these instructions in here. Then we're gonna append not instruction and jump if instruction without like with body end deferred, right? So we can do something like deferred body end. We're gonna just set 0 to it. Then we compile the body, and once we compile the body, we know where it ends. We can go back to this instruction and set the body. That's what we can do in here. That's how we can compile all that stuff. Isn't that cool? Isn't that cool? I think it's pretty cool. So yeah, let's quickly do that. Else is going to be a little bit more complicated, and that's why I'm not implementing it right now. Probably not that complicated, so it should be totally fine. All right, so what I need to do in here, I need to take my condition, right? So here's the condition, and I think for compiling the conditions, we have a special thing. Compile bang expression into bosom. All right, so we provide the bosom, we provide the condition, and also write ID. There we go, and we successfully compiled everything. Right, we successfully compiled everything. If we didn't successfully compile everything, this function will just crash, and we don't have to worry about it afterwards. So the next thing we need to do, we need to push a bunch of instructions afterwards. Right, so we have a special function, push instruction. So we're going to provide the bosom, and what type of instruction we need to push into here? We need to push an instruction not, and I don't remember which one. So it's going to be library bm.h instruction not. Yeah, I think it's a logical not, and we also have a bit. Yeah, so it's a bit one. So we need instruction not, and the operand, it doesn't really have any operand. We can actually set it to 0. It doesn't really matter. Right, and after that we need to push another instruction, which is basically jump if, right, and it also doesn't have any operand yet. It doesn't have any operand yet. Afterwards, we need to remember the where the body starts, I suppose. Do we need to remember that? We need to remember the address of this specific instruction, because we may want to go back to it. So it would be kind of cool if bosom push instruction actually also returned an instruction address. Similarly to how when you push an external native, it returns a native ID. When you push an instruction, it also returns you an instruction address. I think that's a cool idea. Okay, so let's go in here. It's going to be bosom.c instruction address, and this is going to be instruction address. All right, so in this particular case, instruction address is equal to the program size, and we are using this address in here. Then we are incrementing this thing. We can actually do it like this, right? So we incrementing the program size, we're setting the this thing, and then we return the address. Perfect, absolutely perfect. So, and then in the compiler, we can do inst address jump if address, right? So we push the instruction and we remembered its jump if address, so we can go back to it. After that, we need to compile the body, right? So where is my draft? Here it is. So we need to compile the body, and we need to compile it as block, right? Because the body is the block. Compiler.h. So yeah, we compiling block into bosom, right? Just compile block into bosom. So here's the bosom. Block is going to be if then, and we provide the right ID, and there we go. All right. So now the end of the block, is equal to bosom program size. Right, so it's going to be inst address body end address. There we go. This is where body ends. This is precisely where it ends, and what we want to do in here, we want to do bosom program jump if address. We're going back to the jump if address. We take its operand, and we set it toward U64 of body end address. There we go. Believe it or not, this is the entire if compilation. So yeah, that's very interesting. So we're compiling the condition and then pushing a couple of instructions in here. Then we're compiling then block, and we take this thing. Okay, so that's precisely what we're doing here. All right. All right. That's pretty cool. That's pretty cool. All right, so let me see what's going to happen in here. Yep. Unknown function true. Okay, we actually passed this entire stuff. That's actually super cool. So this one is going to be true, and there we go. So all of that kind of compiled. It actually went through like this phase, and now we need to hard code this function. So right now we're actually hard coding all these functions. So let's actually quickly do that as well. So for true, else if this name is equal to true, right? To true, what we're doing is we're gonna just try to compile. I'm gonna just push instruction 1. I think that's precisely what I'm gonna do. I'm gonna just push instruction bosom, instruction push, word U64 1. That's it. So if you have true, we ignore its arguments and we just compile it to just push 1 on the stack. So yeah, that's basically it. And I suppose after that, we'll be able to have something and successfully compiled. So here is the compiled program. Let's take a look at its disassembly. All right, so I'm gonna actually, maybe we also need debosom real quick. So let's recompile debosom. And in here, it's gonna be build tool chain debosom hello BM. It's going to take some time, and there we go. Here is disassembly. Okay, that's actually very cool. Look. We push 1, then we negate it, and we then jump to 6. We jump to 6. Right, so in 6, this is 1, 2, 3, 4, 5, 6. Okay, I suppose maybe this is 0, 1, 2, 3, 4, 5, 6. Right, so essentially here we're actually skipping printing true. Right, so true is located at address 0, and it has 4 characters, and then we print it with a native function. And this entire thing skips it. So technically we implemented if condition, right? So we can try to run this entire thing. So I'm going to do BME, and it's not going to print true. It's actually going to print true. Yeah, there we go. So we actually printed true. Yeah, it's actually printed everything. And maybe here we actually want to have something like a new line. So let's not rebuild anything for now. There we go. So now we have a new line. But also, let's actually implement a false function in here. Right, let's implement false function, and we don't have a false function. Okay, let's go to the compiler and do this similar thing. Right, I'm going to just copy paste this entire stuff. This is going to be false. Right, and in case of a false, we're going to actually push 0 in here. There we go. And we'll need to recompile this entire thing. And as you can see, it didn't print true. It just didn't print true. And if I put true in here and just recompile the entire program and just run it, it actually printed it. And let's put it one more time. It didn't print it. Okay, works. Works perfectly. First try. Cheers, by the way. All right, so maybe we need to yeah, we need to do something with the parsing. All right, so maybe we should implement a special thing that if you encounter true or false, don't expect it to be a function call or something. I think this is going to be useful, but in any case, I think this is worth committing this entire stuff. Let's actually do a committee and then maybe even pushy. To the 2, so this is going to be something like this. A rough implementation of the bang if construction, right? Of the bang if construction. Let's push that right into the repo. Right into the repo. All right. Looks good. Let's take a look at where we parse all of this shit. So I'm pretty sure it's located somewhere in the parsing. To be fair, I'm just thinking, how are we going to handle all of that? So we have AST and different kind of like expressions and whatnot. So maybe for booleans, we need to have a special AST node. Yeah, that's what it feels like. It feels like for booleans, we need to have a special AST node. Let's actually quickly introduce that. So in the parser.h, right, so we should have something like bang expressions, right? Expression kind, yes, a string literal, let's call it boolean literal, right? So it's going to be literal bool. And let's find where we use these kind of things. Maybe I want to actually move it closer to where we use it. I feel like expression kind, yeah. So let's move it in here. So we have a kind like this, and bang fun call. All right, and then if you have a boolean, we're gonna have boolean as bool. There we go. Oh shit, this is actually kind of similar to the statement as pattern. I want to do that actually. I want to rename value to as. Yeah, and I was already using this kind of pattern like implicitly, but as part of the name of the fields. My god, but this way I won't be able to actually do it like that because boolean is already taken, but I can actually do something like boolean. Right, so it's not that big of a deal. It's not that big of a deal. Yeah, so let's actually do a compiler assisted refactoring. I'm going to rename it to as. All right, so it's going to be as. This one is going to be just as. And okay, so let's actually go to the compilation errors and see what's going to happen. All right. So bang expression as. This is because we have a bang expression value, and this has to be called as, not a, but as. There we go. All right, what else do we have in here? So this one has to be something like as. Perfect, look at that. Expression as lead str. My god, this is so good. Feels so good. All right. So maybe I can actually find like a lot of these things and query replace them with the special regular expressions. Oh boy, here we come. Regular expressions. Query replace the regular expression, and I'm gonna replace in. It's hard because I keep forgetting to escape the dots, right? So what I want to capture in here is this, and then this, right? This, and what I want to replace it with, I want to replace it with expression dot as dot one. I wonder if that will be successful. That was not successful, believe it or not. So let me try to do that one more time. Maybe I'm gonna make it a little bit more, like it has to be like a word. Emacs rejects word. How can I match a word? So remember that there was like something like alpha, yeah, so that's what I want. Alpha num. But also, is there something that also matches underscores? Because we also need to underscores. But maybe it's not that difficult to actually implement in here. So you would do something like alpha num, lnum, and then you put underscore in here, and that will, okay, that's precisely what I wanted. Yeah, there we go. Now we're fucking talking. Okay. Good shit. All right. So what do we have in here? Enumeration kind lead bool. All right, so this is the parsing, right? We're trying to compile them. Okay. So that means in here is going to be something like bang, bang expression kind bool. Right, and this one is going to be break, and I think we want to move this kind of stuff in here, right? So it's going to be if expression as boolean, then we're doing bosom push instruction bosom push word u64 otherwise we're pushing 0, right? So that's precisely what we're doing. So these code generation functions are really convenient, right? So you just, you know, traverse the tree and just generating instructions, and that's pretty much it. Very convenient. I really like this design. So expression undeclared lit. Yeah, it has to be like not least but lit. All right, so another one. And it seems to be compiling. Okay, so this is not a function anymore. But we don't parse those things anymore. I see. We don't parse those things. All right, so we need to go to the parser, right? And when we parse bang expression, right? Where do we parse? Okay, here it is. So if the kind name, we automatically assume that this is a function call, right? So we need to do a slightly different thing. If token text is equal to true, right? If it's equal to true, that means this is a boolean, so it has to be bang expression equal to 0, but we are initializing the kind, so it's going to be kind bang expression kind boolean literal, and then as boolean, excuse me, it's going to be true. There we go. Otherwise, if this entire thing is equal to why couldn't I? That's really strange. Excuse me, I forgot to do this thing. Okay, so if this thing is equal to false, right, we're gonna return expression like this, and otherwise we're gonna try to parse it as a fun call. There we go. All right, so now we should be able to do all of that. Expected but got name. What the fuck? Excuse me? So if you're trying to parse bang expression, we actually peek. Okay. So we actually peek, but after we found true or false, we have to straight up like ignore it. Right, so we have to do something like next. And one of the things I want you always to do is just to put a null in here, right? I just want you to put a null in here because I don't really care about this token, but I'm not sure. Maybe I'm going to just provide the token. So if I put a null, I think we don't check for the null in the tokenizer, right? And because of that, it may crash. Yeah, so it's a segmentation fault, I see. So let's put a token in here. So you have to have a token. You must have a token. Okay, so we have a true and So, and then in the compiler, wait, this does not make any sense. This is because I copy-pasted, okay. Okay. Well, it does make sense. I'm trying to parse false, but I'm setting it to true because I copy-pasted this branch. Of course. What else did I expect? I don't know what else did I expect. So it's just, you know. Anyways, so did it change anything? So this is true, right? And then if I change it to, let's actually keep it true, and let's take a look at all of that without the full recompilation, right? Just this, right? So this is the true, and then it's going to be false, and it doesn't exist anymore. And yeah, it doesn't have to be a function anymore, right? So that makes sense to me. So we're now aware of such things as true and false. Absolutely beautiful. Absolutely beautiful. Maybe we should add an else branch. Sounds like a cool idea. So how would you add an else branch? I guess you just compile it after the body end. Wait, really? So let's rename this to then, right? And this one is then, and then else. It's gonna be else. All right. So yeah. Okay. So this is then. Emacs else. Okay. So you have a condition. If not, jump to else. Then in the else you have instructions, and then you have a end if, right? So, and I suppose the additional thing we'll have to do is put unconditional jump to end if. There we go. All right, it's not that hard. I don't like that. So, so here's the condition. If not, we jump to else. Then if you fall through, it jumps to here. Perfect. I think that's the thing we need to add in here. And that way we will be able to even have something like this, right? So it could be something like if true, write true, otherwise write false. That would be actually kind of convenient, I think. I really like that. Really like that. But before we go into that, let's actually do a committee. All right. So what did we do in here? We introduced Boolean literals. So yeah. Implement Boolean literals. There we go. And let's push that right at the repo. This is fun. I really like that. It's just like everything, all of the pieces fit together perfectly. Yeah. Pretty cool. All right, so I want to make a cup of tea. So let's quickly make a small break, and after the break, we're going to implement else branch. All right. All right, I'm back. champion of the arena. So we need to implement the else compilation. We need to implement the else compilation. But before we can implement the else compilation, we need to be able to at least parse the else condition, else branch of the construction. So let's actually try to do something like this. Else, and we're going to put it like this. It's going to be false. All right. So we're getting closer and closer to Turing completeness. My God. All right. So we need to recompile the entire thing and let's go. Let's go. All right. Expected. Okay. So yeah, it didn't recognize this else thingy. And it was trying to parse it as the function call, and that's why it was like that. So let me go to the parser. And where do we pass? Bang if. There we go. This is where we parse bang if. So let me actually look a little bit ahead. Just look a little bit ahead. Can I just reuse this token? I feel like I could have reused this token, but I'm not 100% sure. So I could do something like bang Lexa pick, right? Bang Lexa pick, and we're gonna provide the Lexa, right? And the pointer to this specific token. I think at this point this token is already not needed anymore, but I'm not quite sure. It still kind of makes me wanna like separate this entire stuff, right? Don't really like to reuse the same variables between the logical blocks. It kind of like makes me nervous a little bit, so I'm gonna actually put it like that, right? And we're gonna have our own bang token in here, right? So it's gonna be something like this. It's gonna be zero initialized and stuff like that. And here's the thing: if the token exists and the token kind is equal to bang token kind token kind name, and token text is equal to else, that means we found it. We goddamn found it. We found the else branch. And it feels like this is a pattern. This feels like some sort of a pattern that could have been extracted to some lexing function, similar to like expect next, but this could be expect peak, right? Expect peak, essentially, something like expect keyword peak. But I mean, maybe not right now. We'll see. All right, so we've got the next, and what I want to do in here is probably ignore that thing, right? We want to ignore it. It's gonna be bang Lexa next, provide the Lexa and the token, and I just token it. And I just ignored it. And after that, I'm going to do if else parse curly bang block. It's going to be arena and Alexa. There we go. So we just parsed the else block, right? What we need to do, we just need to check, is there else afterwards? If there is, try to parse the next block. Makes sense to me. So this one is then, and this one is else. There we go. So compilation of our nation. Okay, comrade, and we hit an assertion. There we go. Our compiler does not expect else to have anything. Right. So let's go back to the drawing board and see what we need to do in here. Right. So now this is not so this is jump if address, but interestingly enough, we need to have then. So body and address, I think it got renamed essentially into else address, right? So this is the else address. And that's precisely what we're doing, right? It always jumps to the else. Always jumps to the else. I'm just thinking, where do I have to do that? All right, so after we after we compiled the then, right, after we compiled the then, which is quite interesting, so we are asserting that if then is not equal to null in here, right? So, because otherwise it would be kind of weird. So, and then if else is not null, right? If else is not null, we need to try to compile it one more time. Right, we need to compile one more time, but probably we need to first save the else address, right? We need to save the else address. So, and here's an interesting thing. Here's an interesting thing. As we compile the else address, this one is very interesting. This one is very interesting. It will probably require like changing a lot of this stuff. Don't like that. Don't like that. Let me sip my tea. Just a second. This one is a little bit of a puzzle, right? So basically, if you have else, right? If you have else, you need to include this jump and if. If you don't have else, you don't have to include it. But maybe you can always include it, because if you don't have else, this body is going to be empty. So you're always going to be jumping to the end. So this becomes kind of a useless instruction. But I mean, effectively, the program will act exactly as you want, and we're not implementing any optimizations right now. So maybe kind of stuff like this could be actually optimized away once we have optimizations and whatnot. So maybe we're gonna just generate a code that is a little bit useless when you don't have an else, but at least the compilation step is gonna be easier to generate, I would say. Easier to generate, probably. Probably easier to generate. So, all right. So here is the condition. We're compiling the condition, right? So this one is a condition address rather, right? So this is the condition address. Condition jump if, because I cannot come up with a name for this thing. All right, so maybe here it's going to be like that. Then we're compiling this thing. This becomes an else address, and after compiling the then body, we can always bosom push instruction bosom inst jump if. Just a second, I need to make another break. All right, so my problem with all of that is that the naming is a little bit confusing, right? But we can notice a very interesting thing. At the beginning of then, you have a jump instruction, and at the beginning of else, you also have a jump instruction, and they always jump like forward, right? They always jump forward, and they overlap a little bit. They don't even overlap that much, so maybe you can even make it like this, right? So, yeah, essentially. Maybe not, no. The next one actually like refers to that one, and that one is not okay. Right, they sort of overlap a little bit. So I think this is then jump address, and this is the else jump address. Right, this is the else jump address, and it jumps at the end of this entire stuff. So, and my problem is that I cannot like keep the naming in my head. So, all right, so here's the compilation of the condition. Here is the not, and then this one is going to be then jump address, right? This is then jump address that we are deferring. We're setting it to 0. Okay, cool. Then I'm compiling the then block, right? I'm compiling the then block, and then after the then block is compiled, I need to create an else jump address. So, right, so I need to create an else jump address. So this is going to be the else jump address. But on top of that, I need to save the probably else instruction, just else address. So this is the else jump address, right? This is the else jump address. At the end of this thing, then jump address, and what is that? It's precisely what it is. And then we need to save the else address, and the else address, right? Else address is going to be equal to the bosom program size, right? It's going to be equal to the bosom program size. So here it is. After that, if you have an else, right? If you have an else, you're going to be compiling this entire thing, right? You're going to be compiling this entire thing like so. Compile block into bosom, right? It's going to be bosom if else, right? It actually has to be else right ID. And after that, we need to have something like end address. So inst address end address is going to be bosom program size, right? All right, that looks okay. I wonder if you compile an empty block, a block that doesn't exist, what's going to happen? Nothing's going to happen. Maybe because of that, we can just remove this entire thing. That doesn't sound like a bad idea, actually. Wait a second. Right, so if else doesn't exist, it's not going to fail or anything. And maybe, yeah, that's perfect. Okay, so we are compiling the condition. We put a not in here, and then we push jump if in there, right? We push jump if in there. So this is a then jump instruction. Then we compile then block. So all of that corresponds to that. So jump if, then we don't need to remember then we compile this thing, right? And we put else jump instruction. By the way, else jump instruction is unconditional jump. So then we remember else address, right? We remember else address. Then we compile else. If it's empty, and then we remember the end address. So I might as well actually put it like end. Right, so we have then else and end. All right, so we compiled everything, but now we need to wire up these jump ifs, right? So what I need to do now, right, I need to find bosom program, and here we have a then jump address, right? So this is a then jump address. We take its operand, and we set it to word u64. It has to jump to else address, right? So this is going to be else address, right? This is a then jump address. We're setting it to else address. We don't know any of these addresses until we finished compilation. So first we have to compile everything, and only then we can wire everything up. Right, so all of these things are deferred for now. Right, and after that, we need to find the else jump. Right, we need to find the else. So it's going to be bosom program else jump address, and we set it to the operand word u64 end address. Okay. All right, so that's a little bit better. That is a little bit better. We compile the condition, then jump address. Okay, we push this thing. Compile the body, then we add a jump. So it's an else jump address. So then we take the else address, which is after the jump, combine the else, and we find the end, and then we wire everything. Like, hopefully I didn't make any mistakes. We'll see how it goes. We'll see how it goes. All right, so let me try to compile this entire stuff, and let's see. All right, so it printed true, which is very interesting. Right, it prints true. What if I go now to hello bang? Hello bang. All right, it is in fact prints true. What if I set it to false? It prints false now. Yeah, it flip-flops now. That's actually perfect. Huh. What if I have 3 truths in here? Right, it prints true, but then it's going to print a single false. It's perfect. It works. It actually works. What the fuck? That's super nice. That is in fact super nice. Cheers. That's cool. What about elseless? How about some elseless stuff? So if I remove this thing, it works. If I make it true, it also works. Yeah, so you can have else, you may not have else, and everything is working precisely as it should. That's nice. Then it's gonna be false. Cool. So let's keep it like that. Right. So when it's okay, that's interesting. Yeah, perfect. It's gonna be true. Yeah, Emacs, what the fuck are you doing? Yeah, all right, everything seems to be working. So let me also put a hello bang in here. Hello bang. Just to demonstrate how our language works, and everything seems to be working. All right, so let's do a committee. Okay, implement else for the bang if construction, and I'm gonna push that right into the repo. Let's do the full recompilation just to check if everything's okay. And yeah, we implemented if conditions. Isn't that exciting? I think it's goddamn fucking exciting, mate. All right, so let's compare and pull request. Bang if. Okay, something is failing somewhere already. Is it because of the formatting? We're about to find out. Probably because formatting. Yeah, formatting. Okay, let's actually fix formatting super quick. It's gonna be just FMT, and what we got? Oh yeah, classic. Fix for matching remarks. Right, and let's push that right into the repo. All right. The next step, by the way, would be implementing something like a while loop. And I think, from my perspective, a while loop is basically elseless if that is repeated more than one time, right? There is an interesting isomorphism between while and if, right? If is just like a while, but it does only one iteration, but while performs several iterations. So maybe because of that, implementing a while loop is going to be relatively straightforward. It's just like elseless if, but at the end of this thing, you just like jump back to checking condition. But it's kind of pointless unless you have a mutable variables, if you know what I mean. It's kind of useless until you have that. So maybe the next thing we need to introduce is just like mutable variables. But implementing mutable variables like on the stack or as the arguments is kind of a big task for now. I could try to implement some variables, I don't know, global variables, right? So we could have something like this, int 32 or int 64, right, 0. And then we could implement an assignment, right? So you would initialize it to 0. Then you would check x, I don't know, while x is less than 10, you would print that, and then you would increment it like by 1 or something. Something like that. Something like that. Or maybe we're not going to use this assignment operator. I don't know. Right, so what that means, we need to implement an AST node for declaring a variable, then for assigning a variable, then also for reading a variable and writing the variable, right? So and also less than 10. So this is there's a lot of things involved in here, right? There's really like a lot of things involved to implement a while loop. So maybe we can have some sort of a shortcut. It would be kind of nice to have some sort of a shortcut. Maybe we could implement like a hard-coded global variable that is always defined for you. And for instance, right, we can actually hardcode that variable. That's very interesting. Right. So every time you refer to the name X, right, every time you refer to the name X, you are referring to that variable, and we keep it in the memory. Then we'll need to only implement parsing of the of the number literals and comparison, right? And then we can have some sort of a function inc_x, which increments the x by 1, right? And there is a lot of hard-coded stuff in here just to test the while loops without implementing all of these concepts yet. That would be interesting, right? That would be interesting. It's still a lot of work, actually. It is still a lot of work. One of the things we can do is we can cut off on implementing comparison for now, right? So we're not going to implement comparison. So we're going to implement only x, right? And then we could implement a function that sets x to, yeah, we still need to implement parsing the numbers, but we can implement only integers, right? We can only implement like integer literals, right? And then we can implement dec. So we already know how to parse functions with a single argument, so we can need to implement functions with no argument. Yeah, so this is something that is pretty feasible to implement relatively quick, I would say. Relatively quick. But then if we're going to have an x, right, so we probably need to allocate it somewhere in a static memory, right? We need to allocate it somewhere in a static memory. So we can easily do that the same way as we allocate strings. We just can allocate 8 bytes, right, and treat those 8 bytes as the number, right? But yeah, not really sure if I have enough time to do all of that, but that will be actually very interesting. That would be actually very interesting. Okay, I think this one is done, so let's quickly do that. To be fair, it's kind of difficult to work with bank right now because it doesn't have a context, right? So, and this thing really wants to have a context. For instance, you want to store native ID, write ID in that specific context. Maybe this is something that I'm going to introduce first, right? So in a bank compiler, right? So we're going to have a bank compiler, right? And what this thing is going to have is going to have its own structure in here, right? Which is going to be just bang. Right, and for now it's gonna store this native ID, write ID, right? So that's basically the refactoring that I want to have. And then in here we would also store the memory address to the global X, right? And so we can pass it around. Yeah, so obviously this thing wants to like keep some sort of a context that you can pass around all the time, because yeah, so let's quickly do that. What am I thinking is that we need to have some sort of function that initializes this write ID. All right. We can do something like compile bank begin, right? And you would provide the pointer to the bang. And maybe we can also have something like end, which will finalize, like add I don't know, halt in there or something. But I'm not sure, maybe end is not needed in here. Yeah, so let's just keep it like that. Okay, so let me see. So the compiler C, and when we're starting the compilation, essentially, so proc definition, right? So where's the proc definition? Push native boson push external. Where do we do external native? Push external. Oh, we do that out. Okay, I see. I'll probably do that outside. All right, let me actually quickly refactor this entire stuff. So the way we're going to refactor all of that, we're going to remove all of these native IDs, and set them like this, and then I'm going to select all of these things and add bang, bang, like so. Right, so then inside of the compiler, I want to get rid of all of those things. Right, it's going to be query replace that with nothing, boom. And then I want to find all of these things and query replace them with bang, bang, bosom, bosom. I guess that's going to be it. Seems to be working. And let's actually go through the compilation errors and see what we have. Yep. And so you don't need to pass the right ID in there, but you have to pass bang in here. Bang right ID. All right. Wait, this is a okay. This is a pointer. That makes sense. Yes. All right. This is not needed. Bang. Maybe we should go through all the compilations things. Yep. Bang. Compile block into dozen. I can see it. So this stuff is not needed, and then we're gonna do bang. This is also not needed. All right. Okay, so we are in bang in here. So what I need to do in here is rather bang, bang, 0 initialize it, and then assign right ID to that, and then just something like this, and this one is going to be bang. There we go. Should be pretty straightforward. Okay. All right, so yeah, I refactored everything. So now we have a special context that is passed around, and we can put things into that context. Specifically, what I wanted to put into that context is variable x, right? So how can we even do that? You see, we push an external native into the memory, into the a list of external natives, and in here in the compiler, we're going to introduce a memory address for x, right? And it's going to be a similar thing. So it's going to be bang x. Maybe it should be called address. Right? X address, and the way it works in the bosom code generator, we have something like push. I don't remember. There was like a push string to memory. You can push byte array to memory. You can push specific buffer into the. Okay, so you can. Yeah. So let's call this function, right? Let's call this function. So we provide the bosom, and the size of the thing that we're going to push in there is going to be size of uint64, right? So we're allocating a variable in a static memory, and we're initializing everything with 0. And of course, this has to be something like as u64 or something like that, or something close. And there we go. We have an address to the global x variable. There we go. So this is it's unknown memory address. Very interesting. So we really don't have memory addresses in there. So where is the native ID? Oh, it's literally called memory address. Okay, sure, fine. I forgot about that. So okay, cool. Oh, wait a second. Why is it not working? All right. So probably something like this. Well, the point is in here is that when you try to access x, right? When you try to access x, it should read from that address in the memory, right? It should read from that address in the memory. So let me think, but that will require adding that will require adding a special AST node for the variables. This looks like a lot of work, actually. Let's actually leave implementing while loops for the next stream, right? Let's actually do it for the next stream, because that's a lot of work, right? Even though I'm trying to cut down on as many things to implement as possible, right? You still need to have a lot of things to actually properly test while loops. Right, so the only useful thing I got out of this is the context, right? So we introduced the context, and this is quite important. So let's actually do a pull request for this change. All right, so I'm going to remove that, and let's take a look. All right, and let me get the original thing in here. And there we go. So we have a false, a hello bang. And yeah, we implemented conditions. Isn't that cool? Isn't that cool? I think it's goddamn fucking cool, mate. So yeah. Oh, wait a second. Oh my god, I forgot to fetch the latest changes. All right, just a second. I'm gonna go to the master, fetch the latest changes, because I already merged the pull request. Yeah. All right, merge the master, and there we go. Really? What the hell are you talking about? It says that this thing is merged. Okay, I think I was too fast. Bang. Context. All right, so and in here I'm gonna unstash this entire thing, and we're gonna say something like introduce bang compilation context. All right, and let's push that right into the repo. Yes, and we're gonna create another pull request. Yet another pull request. Our language becoming stronger and stronger every goddamn day. It's beautiful. It's absolutely beautiful. Soon it will take over the world. Oh. It's almost time to think about our propaganda plan, right? So if you're creating a new language in 2021, you won't be able to make it successful unless you push it with a very powerful, overbearing propaganda. So, what do you guys think? What should be the propaganda plan for our language to make everyone use it? I don't know. Probably something. Okay, so if I learned anything within these 2 to 3 weeks of YouTube, is that it doesn't fucking matter what you're doing. All of that goes to shit if you don't have a good thumbnail and a good title. So what we're gonna do right now, we're gonna try to come up with a good thumbnail. So I think this could be a pretty good thumbnail. So let me actually have it like that. All right. As you can see, there is a little bit of a mystery in here, right? So there's a true, but it prints false, and in else it prints true. Like, what the fuck? So, and to make it a little bit more interesting, I'm gonna actually, you know, increase my camera, size of my camera, and have like a surprised face or something like that. I don't know. Was it good? Was it clickbaity enough? Or something like that. I don't know how to do YouTube. I'm sorry. So anyway, that's it for today. Sorry. That's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow is a Friday, if I'm not mistaken, right? Tomorrow is a Friday. And that means tomorrow I'm gonna pick a random topic that I want you to, you know, learn, and I'm gonna do the whole video, the whole session on that specific token, and that topic is a secret. You'll have to watch the video. You'll have to click the video to know what's gonna be the topic. Anyway, thanks everyone for watching. Love you all. Mwah.